I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to see some numericals based on charge carrier concentration. So let us have a quick recap of the formulae that we are going to use. So the first one is N. N here represents the concentration of electrons in the conduction band is given by 2 into 2 pi me kbt by h square power 3 by 2 into e power ef minus ec by kbt. I will tell you the terms that we are using here so that we will be using the same terms again and again. So N here represents the concentration of electrons. Concentration of electrons in conduction band. 2 pi are constants. Me here represents the mass. Here we call it as actually Me star, which is nothing but the rest mass of an electron. Or we also call it as effective mass of electron. And Kb here is the Boltzmann constant. It is a constant which was given by Boltzmann. So we are using that constant here. Kb is the Boltzmann constant. T is the temperature which we always consider in SI unit. That is in degree Kelvin. T is the temperature and H here is the Planck's constant. H is the Planck's constant. EF represents the Fermi level. EF is the Fermi level. And EC represents the lowest level in conduction band. EC represents the lowest level in conduction band. Kb and T we have already represented. Next comes the formula for P. P here represents the concentration of holes in the valence band. That is given by 2 into 2 pi mp star kbt by h square power 3 by 2 into e power ev minus ef upon kbt. So all the other terms are known here. P represents the concentration of holes in valence band. And MP star represents the effective mass of holes. Effective mass of holes. And EV represents the highest level in valence band. EV is the highest level in valence band. Now we are going to write the formula for intrinsic carrier concentration. Actually, when you see an intrinsic semiconductor, always the number of electrons in the conduction band is equal to the number of holes in the valence band. And when we talk about the intrinsic carrier concentration, Ni, which is given by N into P, we get Ni is equal to 2 into 2 pi m kbt by h square. Here I may write it as m naught, which is the rest mass, upon kbt by upon h square power 3 by 2 into e power minus eg upon 2 kbt. 2 pi kb h m naught, all these are constants. Eg here represents the energy gap between the valence band and the conduction band. Eg here represents what? Eg represents the energy gap. Then we have a formula for Fermi level. To find the Fermi level, we use EF is equal to EC plus EV by 2 plus 3 by 4 kBT ln mH star upon me star. So all are known terms. EC is the lowest level in conduction band, we have written here. EV represents the highest level in valence band, we have written. Kb is the Boltzmann constant, T is the temperature in Kelvin. mH or MP, here we are writing it as MP for holes, we can also write it as mH also. mH upon me. mH represents the mass of the hole, effective mass. Me represents the effective mass of the electron. Now, at any temperature, T is equal to 0 Kelvin. If you are taking this T equal to 0, this entire term vanishes and we have EF is equal to simply EC plus EV by 2. That means what? The Fermi level lies exactly in between EC and EV. That means lies in between the energy gap. That is what we understand at T is equal to 0 Kelvin. Then we will also see a simple formula which is Ni square is equal to N into P. Means if you want to find the concentration of electrons knowing the intrinsic carrier concentration, so this implies N will be equal to Ni square upon P and P will be equal to Ni square upon N. So this formula will be useful to calculate the concentration of electrons knowing the intrinsic carrier concentration and the concentration of holes. And here to find the concentration of holes, you know the intrinsic carrier concentration and also the concentration of electrons. So these are the formulae which we are going to use now to do the numericals. Now coming to the first numerical. For an intrinsic semiconductor with a band gap of Eg is equal to 0.7 electron volt, calculate the intrinsic carrier concentration at 37 degrees Celsius. If Me is equal to Mp is equal to M naught, means the rest mass of the electron is equal to the rest mass of the hole is equal to the M naught. So rest mass of the electron M naught. So what we have to calculate here, calculate the intrinsic carrier concentration. So first let us write the data given. What is the data that is given and what we have to find. What is the data given? Eg. Eg is equal to 0.7 electron volt. So whenever we have this in electron volt, we need to convert it into joules because we are doing the entire numerical in SI system. So in SI system, the energy is measured in joules. So what is the conversion for 1 electron volt? 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So I am going to convert this 0.7 electron volt to joules by multiplying it with 1.6 into 10 to the power of minus 19. So the energy is now in joules, expressed in joules. Then the temperature is given. What is the temperature here? T is equal to 37 degrees Celsius. We are going to convert it into Kelvin. So this will be 37 plus 273. So this will be 310 degree Kelvin. This is in Kelvin, the temperature. And then Me is equal to Mp is equal to M naught, which is the rest mass of the electron. So what is the rest mass of the electron? 9.1 into 10 to the power of minus 31 kilograms. And what we have to find here is the intrinsic carrier concentration Ni. We have to find. And also we are going to use one more constant Kb. 1.38 into 10 to the power of minus 23 joules per Kelvin. This is one constant we are going to use. And we also have the Planck's constant H is equal to 6.625 into 10 to the power of minus 34 joule seconds. So we are going to use this constant also. So write the formula for Ni. So what we have discussed before, the formula we are going to use the same. Ni is equal to 2 into 2 pi m naught kBt by h square power 3 by 2 into e power minus eg upon 2 kBt. This is the formula we are going to use, and we have discussed all the terms. M naught is the rest mass given by 9.1 into 10 power minus 31. Kb is a constant given by 1.38 into 10 power minus 23. T is the temperature which we have converted into Kelvin, 310 Kelvin. H is again a constant, 6.625 into 10 power minus 34. And Eg is given 0.7 electron volt, which we have converted into joules. So Kb and T we have. So let us do the substitution now. So Ni is equal to 2 into 2. The value of pi we are taking as 3.14 into rest mass of the electron 9.1 into 10 power minus 31 into Kb 1.38 into 10 to the power of minus 23. The temperature is 310 upon h square 6.625 into 10 power minus 34 square e power minus Eg. What is the value of Eg we have? 0.7 into 1.6 into 10 power minus 19 by 2 into 1.38 into 10 power minus 23 into T is 310. So we are going to simplify this. First you can simplify this exponential term. You can use your calculator to simplify and then multiply it with this. So we get the value of Ni as 5.429 into 10 power 19 per meter cube. Means the intrinsic carrier concentration. Means intrinsic carrier concentration here means the charge carrier density. The number of charge carriers per unit volume is 5.429 into 10 power 19 per meter cube. So this is expressed in per unit volume. So per meter cube. So what are the steps we have followed? First, you should be writing the data that is given. What is the data given? And do the appropriate conversion. If you are doing in the SI system, all the quantities that are given have to be expressed in SI system. Then write the formula, which formula we are going to use here, and then do the substitution, simplify, get the result, write the result along with the answer. Unit. Now coming to the second one. Calculate the intrinsic charge carrier concentration for germanium at 27 degrees Celsius and the band gap is 0.7 electron volt. So this is similar to the previous one. Only thing is the temperature here is varying. So we will try to understand what happens with the increase in temperature or with the decrease. There it was 37, here it is 27. When the temperature is lowered, how the charge carrier concentration varies, we can understand with the help of this numerical. Now the data given. Band gap Eg 0.7 electron volt. So we will convert it into joules by multiplying it with 1.6 into 10 power minus 19, because 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So Eg is given by 0.7 into 1.6 into 10 power minus 19 joules. The temperature T is equal to 27 degrees Celsius. So 27 we are going to convert it into Kelvin by adding 273. So this will be 300 Kelvin. So the temperature is 300 Kelvin. And of course we are going to use the constants Kb, 1.38 into 10 power minus 23 joules per Kelvin. The value of H, 6.625 into 10 power minus 34 joule seconds. And also we have to use m naught, the rest mass of an electron, 9.1 into 10 power minus 31 kilograms. So all these constants, in some questions the constants may be mentioned, but otherwise for these numericals you need to remember these constant values. Once you do a number of numericals, these values you will be able to memorize them and use them here in doing the numericals. So what we have to calculate here, calculate the intrinsic charge carrier concentration, means we have to find Ni. What is Ni equal to? So let us write the formula for Ni. So this is the second step. The first step is the data given. Second step is writing the appropriate formula. So what is the formula? Ni is equal to 2 into 2 pi m naught kBt by h square power 3 by 2 e power minus eg by 2 kBt. So we need to substitute now in this formula. So what is Ni equal to? 2 into 2 into 3.14, and the rest mass of the electron 9.1 into 10 power minus 31, and Kb is 1.38 into 10 power minus 23 into temperature 300 Kelvin divided by 6.625 into 10 power minus 34 whole square power 3 by 2 e power minus Eg. Eg is what? 0.7 into 1.6 into 10 power minus 19 by 2 into Kb. Kb is Boltzmann constant, 1.38 into 10 power minus 23 into T is 300 Kelvin. So when we do the simplification, what we are going to get here is 33.49 into 10 power 18. So the number of charges per unit volume is 33.49 into 10 power 18 per meter cube. So we have got the intrinsic charge carrier concentration, that is nothing but the number of charge carriers per unit volume. Now coming to the third numerical. What temperature would the Fermi level EF be shifted by 15% from the middle of the forbidden gap given Eg is equal to 1.2 electron volt and the effective mass of the hole is 5 times that of the electrons? So here you need to understand the theory before you do the numerical. So let me give you the theory behind this numerical. So when we are talking about an intrinsic semiconductor, so if this is the valence band, this is the topmost level of the valence band EV, and if this is the conduction band, this is the lowest level of the conduction band EC, and this is what we call it as EG. That is the gap between the conduction band. This is the conduction band and this is the valence band. Now, for an intrinsic semiconductor, at T is equal to 0 Kelvin, the Fermi level lies exactly in between, EF. So, I have given you the formula also. EF is equal to EC plus EV by 2. Means the Fermi level lies exactly in between the energy gap in case of an intrinsic semiconductor at 0 Kelvin. Now, what they are talking about, what temperature would the Fermi level be shifted by 15% from the middle of the Fermi gap? Means when the Fermi level is here at 0 Kelvin, if the temperature increases, the Fermi level slightly shifts towards the conduction band. That is the theory behind. Now, when the temperature increases, at what temperature will it shift by 15%? That is what we have to find. So, if the Fermi level is here, if it has to shift by 15%, what temperature it will happen? At what temperature it will shift by 15%? That is what we have to find out. What is the gap given by here? Eg is equal to 1.2 electron volt. So, the effective mass of the hole is 5 times that of the electron. I hope you understood what is given and what we have to find. So, let us write it very clearly. Given data, EF is shifting by 15%. What temperature it is shifting? We have to find. Eg is equal to 1.2 electron volt. And effective mass of the hole is 5 times that of the electron. So, mH star is equal to 5 times me star. 5 times that of the electron. And we have to find the temperature. Okay. So, what is the formula we are going to use now? EF is equal to EC plus EV by 2 plus 3 by 4 kBT ln mH star by m. So, this is the formula we are going to use. Okay. And we have to find the value of T. So, how do we apply the given data now? First thing what we are going to write is EF is equal to EC plus EV by 2. This is at 0 Kelvin. I have written the formula. This is at 0 Kelvin. This is at the center. Now, I can also write it in another way. If I am talking about this is the Fermi level and Fermi level lies exactly in between the energy gap, Eg. Eg is equal to 1.2. So, what will Eg by 2 be equal to? 0.6 electron volt. So, this part will be equal to 0.6 electron volt. So, EV plus 0.6 will give me the Fermi level. So, I will write it as EV plus 0.6. Hope you understood. Because the Fermi level lies exactly in between the energy gap and the energy gap is given as 1.2 electron volt. So, we are writing EV plus 0.6 must be equal to EC plus EV by 2. Now, what they are telling it is 15%. 15% of what? 15% of 1.2. What is the energy gap here? 1.2 electron volt. So, what is 15% of 1.2? 15% of 1.2 will be 0.18 electron volt. This is also an electron volt. Because of the increase in temperature, so at T Kelvin, at T degree Kelvin, it is shifting by 15%. So, 15% of 1.2 will be 0.18. So where will the Fermi level now be? It will be at EV plus 0.6 plus 0.18. So 0.78. I hope you understood. I will take this as equation 1 and we'll take this as equation 2. Means and as the temperature increases, it is increasing by, it is shifting by 15%, that is 0.18. Actually it is at 0.6. Now it is moving by 0.18. So it will be EV plus 0.78 will be equal to EC plus EV by 2 plus 3 by 4 kBT ln mH by ME. mH is what? 5 times ME upon M. We'll take this as equation 2. Equation 1 we have EC plus EV by 2 is equal to EV plus 0.6. So I will rewrite it here as EV plus 0.6 is equal to EC plus EV by 2, just by interchanging the terms for convenience. This is 1 representing the same equation. Now if I can subtract equation 1 from equation 2. If we are subtracting this equation 1 from equation 2, EV gets cancelled. 0.78 minus 0.6 will be 0.18. EC plus EV by 2 and minus EC plus EV by 2 will get cancelled. This will be 3 by 4 kBT ln ME and ME will get cancelled and you have 5. So 0.48 is equal to 3 by 4 kBT ln 5. We have to find T. So I'm going to write the formula for T. Rearrange the terms and write for T. So T will be equal to what? 4 by 3 into 0.18 upon kb ln 5. We have 0.18 here. We are taking 4 onto the other side. 3 comes to the denominator. kb is in the numerator. Ln 5 is in the numerator. So it comes down. Now this 0.18 is an electron volt. So we need to convert it into joules. So I will multiply it with 1.6 into 10 power minus 19. So T is equal to 4 by 3 into 0.18 into 1.6 into 10 power minus 19. Now we are going to substitute the value of kb also. 4 by 3 into 0.18 into 1.6 into 10 power minus 19 divided by, what is the value of kb? 1.38 into 10 power minus 23 into ln 5. You can use the calc directly, get the value of ln 5, substitute here and you get T is equal to 1729 Kelvin. So at this temperature, 1729 Kelvin, the Fermi level will shift by 15%. 15% of 1.2 electron volt. Now coming to the fourth one. For silicon, Eg is equal to 1.12 electron volt. Find EF at 300 Kelvin. Given that Me is equal to 0.12 M naught and MH is equal to 0.28 M naught. What we have to find here? We have to find the Fermi level. So write the data. Eg is equal to 1.12 electron volt. So this will be 1.12 into 1.6 into 10 to the power of minus 19 joules. This is the value of Eg. E temperature is equal to 300 Kelvin. Me star is equal to 0.12 M naught. And mH star is equal to 0.28 M naught. Find EF. So let us write the formula for EF. EF is equal to EC plus EV by 2 plus 3 by 4 kBT ln mH by me star. Okay. Now we are not given the values of EC and EV, we are given EG. So how do we write it in terms of VG? We'll understand with the help of the diagram again. We will take the energy level diagram. This is the valence band. This is the conduction band. Now the Fermi level is here, EF, exactly at between at 0 Kelvin, EV and EC. So we have to find EF at 300 Kelvin. So from here, how much it is going to shift, we have to find the position of the Fermi level. So how we are going to do it is, in terms of EG, we have to write. Now, this is EV plus EG by 2 I can write here. What is the position of EF here? This is nothing but EG by 2. If I have to write the position of the Fermi level, I can clearly write it as EV plus EG by 2. EC plus EV by 2 can also be written as EV plus EG by 2. That gives us the value or the position of the Fermi level. So now I write here EF is equal to EV plus EG by 2 plus 3 by 4 kBT ln mH star upon me star. So I have modified the formula as per the data given. EC and EV we do not know, so we are writing it in terms of EG. So how do we write now? EF is equal to EV plus EG. What is the value of EG? 1.12. If we are going to find it in electron volt, we can simply neglect this and write it in 1.12 electron volt also. So I am doing it in electron volt. So 1.12 by 2 plus 3 by 4. The value of KB is 1.38 into 10 power minus 23. Because I have kept this in electron volt, I will write this value of KB also in electron volt by dividing it with 1.6 into 10 power minus 19 into temperature. Temperature is given as 300 ln mH is 0.28 m naught and me is 0.12 m naught. So m naught will get cancelled. EF will be equal to EV plus 0.6 plus 3 by 4. I'll keep it as 1.12 by 2 only. We can use the calci to find the value. 1.12 by 2 into 1.38 into 10 power minus 23 by 1.6 into 10 power minus 19 into 300 into ln, simply we have 0.28 upon 0.12. So simplify all these values, we get EF is equal to EV plus 0.576 electron volt. So we are getting the answer in electron volt. So where does the Fermi level lie? It will lie at 0.576 electron volt above EV. Okay. So that is how we are expressing it in terms of electron volt. If this is EV, so it will lie at a distance of 0.576 electron volt above EV. Next, calculate the intrinsic concentration of charge carriers at 300 Kelvin given that Me is equal to 0.12 M naught, MH is equal to 0.28 M naught and the value of band gap is 0.67 eV. So let us first write the data. Temperature is given, T is equal to 300 Kelvin temperature. Then the rest mass of the electron, Me is 0.12 M naught. MH star is 0.28 M naught. And EG, the band gap is 0.67 electron volt. We have to find Ni. Ni is equal to what? We have the formula for Ni. The formula for Ni here is Ni is equal to 2 pi M naught kBT by H square power 3 by 2 into e power minus Eg by 2 kBT. So this is the formula. But we need to modify this formula slightly because this is the formula after approximating that Me star is equal to Me star is equal to M naught. We have made an approximation that the rest effective mass of the hole is equal to the effective mass of the electron is equal to M naught. So whenever we do MH into Me is equal to M naught, if I have to write MH into Me, so that will be M naught into M naught, that will be equal to M naught square. So when we are having here M naught square and we have power 3 by 2. So how did we get power 3 by 2 is because we have M naught by 3 by 4 power square. So we are neglecting or cancelling and we are writing M naught power 3 by 2. So we have M naught inside 3 by 2. But otherwise what we have to write? M naught MH into Me power 3 by 4. So since the values of MH and Me are not the same, I am going to write this formula as taking M naught out. 2 pi kBT by H square power 3 by 2 into Me into MH power 3 by 4. Because these two are same, M naught square power 3 by 4, we have got 3 by 2 and we have taken it inside. But because they are not same in the given problem, we are bringing them outside. So we get Me into MH power 3 by 4 e power minus Eg by 2 kBT. You need to understand how the formula gets modified with the data given. So we can write Ni is equal to, do the substitution, 2 into 2 into 3.14 into 1.38 into 10 power minus 34 into 300 divided by 6.625 into 10 power, sorry, this is minus 23, minus 34 whole square power 3 by 2. We are going to substitute the values of Me and MH. Me is equal to 0.12 into M naught. M naught is the rest mass. 9.1 into 10 power minus 31 into 0.28 into M naught. 9.1 into 10 power minus 31 whole power 3 by 4. This whole thing, this is M naught into Me. 0.12 M naught. 0.28 M naught into e power minus Eg. Eg is now 0.67 into 1.6 into 10 power minus 19 divided by 2 into 1.38 into 10 power minus 23 into 300. So all this is the exponential term. So simplify, we get Ni is equal to 2.3407 into 10 power 18 per meter cube. So the number of charge carriers per unit volume is given by 2.3407 into 10 power 18 per meter cube. Now, for an intrinsic semiconductor with a band gap of 0.7 electron volt, determine the position of EF at T is equal to 300 Kelvin if mH is equal to 6 times Me. So, similar to the one we did before. So, data given. Eg is equal to 0.7 electron volt. Temperature is 300 Kelvin. mH star is equal to 6 Me star. Slight modification in data. mH star, the mass, effective mass of the hole is 6 times the mass of the electron. We have to find EF. So the formula we are going to use is the same. EF is equal to EC plus EV by 2 plus 3 by 4 kBT ln mH star by M star. Again, we do not have EC and EV. So what we are going to do? We are going to modify it. This is the valence band. This is the conduction band. EC, EV. This is EG. The Fermi level lies exactly here. EF, where EF is equal to EC plus EV by 2. Or if I have to write the position of this, it is above EV. So we can write it as EV plus EG by 2 also. If I have to locate the position, we will write it as EV. Above EV you have EG and half of it. So this is EV and this is EG by 2. So EV plus EG by 2. So we will write it as EV plus EG by 2 plus 3 by 4 kBT ln mH is 6 times Me star. So Me will get cancelled. So substitute for EG now. EF is equal to EV plus 0.7 by 2 plus 3 by 4 kBT is 1.38 into 10 power minus 23 divided by 1.6 into 10 power minus 19. Because we have taken the value of Eg in electron volt, we are converting this joules also into electron volt into ln 6. So we will get EF is equal to EV plus 0.3847 electron volt. So the Fermi level lies 0.3847 electron volts above EV. Okay, that will be the position of the Fermi level. Now coming to the next one. In a p-type silicon sample, the whole concentration is 2.25 into 10 power 15 per centimeter cube. The intrinsic carrier concentration is 1.5 into 10 power 10 centimeter cube. Find the electron concentration. It's a very simple numerical. So first we'll write the data. Whole concentration is given. So the whole concentration is represented by P. P is 2.25 into 10 power 15 per centimeter cube. Here it is given in CGS system per centimeter cube. And the intrinsic carrier concentration, that is Ni. Ni is 1.5 into 10 power 10 per centimeter cube. So both are in SI system. There is no problem. We can continue doing the numerical in CGS system. So find the electron concentration, that is N. We have to find N. So what is the formula we are going to use? Ni square is equal to N into P. Whole concentration is given, intrinsic is given, we have to find N. So I'll write the formula for N as Ni square upon P. Ni square upon P. So what is the value of Ni? 1.5 into 10 power 10 into 1.5 into 10 power 10. Ni square divided by P is 2.25 into 10 power 15. Here we can simplify it very easily. 1.5 into 1.5 is 2.25. 10 power 10 into 10 power 10 is 10 power 20. Divided by 2.25 into 10 power 15. So this will get cancelled. 10 power 20 by 10 power 15. Take to the numerator, 20 minus 15, we get 10 power 5. So this will give us N is equal to 10 power 5 per centimeter cube. So the answer also will be in CGS, that is per centimeter cube. So the concentration of electrons is 10 power 5 per centimeter cube. Now one more. The intrinsic carrier concentration of the silicon sample at 300 Kelvin is 1.5 into 10 power 16 per meter cube. If after doping, the number of majority carriers is 5 into 10 power 20 per meter cube, calculate the minority carrier density. Here we are talking in terms of majority and minority. So in case of N-type, the majority carriers are electrons and the minority carriers are holes. And if you take it for a P-type, the majority carriers are holes and the minority carriers are electrons. So we will use that concept and we will write the data and calculate the minority carrier density. So the intrinsic carrier concentration is Ni is equal to 1.5 into 10 power 16 per meter cube. This is in SI system. After doping the majority carriers, so if I am taking as N-type, the majority carriers are electrons. So I will write for N as 5 into 10 power 20 per meter cube. We have to calculate the minority carrier density. So the minority carriers will be holes. So what will P be equal to? So the formula, Ni square is equal to N into P. We have to find P here. P is equal to Ni square upon N. So what is the value of Ni square? 1.5 into 10 power 16 into 1.5 into 10 power 16 divided by 5 into 10 power 20. So here you have 2.25 by 5 into 10 power 32 by 10 power 20. So you will get it as 4.5 into 10 power 11 per meter cube. So the minority carrier density means the number of holes per unit volume is given by 4.5 into 10 power 11 per meter cube. Okay. We will continue with the next topics in the next class. So keep in touch. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.